OCR Chemistry A, benzene and aromatic compounds, structure and electrophilic substitutions. Getting the most from Chemistry Explained means taking notes and completing tasks on paper or on a tablet, controlling the pace at which the lesson proceeds. Particularly when prompted, pause the lesson, complete the task, thinking it through, taking your time. When you're ready, return to the lesson and correct your work before proceeding. So this lesson will cover the Kekule model of benzene and why it needs to be replaced by the delocalised electron model of benzene. We'll then move on to naming aromatics and then the typical reactions of the benzene ring, which are electrophilic substitutions. So let's start with some basic information about benzene. So benzene is a molecule with the formula C6H6. And where does the word aromatic come from? Well, any compound containing one benzene molecule or one benzene structure, or as we will see, one benzene ring or more, are called aromatics. If the aromatic, that is the molecule containing one or more benzene rings, is a hydrocarbon containing carbon and hydrogen only, then an additional piece of vocab is that those groups of molecules which are aromatic yet hydrocarbon are called arenes. We will initially start to discuss the chemistry of benzene through the Kekule model. Now Kekule, as you will read, pondered long and hard on how on earth 6 carbons and 6 hydrogens could form a stable molecule, and he proposed a ring structure which consisted of a 6 carbon ring, obviously C6H6, with alternate single and double carbon bonds. No similar structure had ever been discovered or proposed before. So it was a remarkable idea, and if we put that into a displayed diagram, there is the Kekule model as thought. Alternate single and double bonds, 6 carbons, carbon double bond, carbon, carbon single bond, carbon, and so on. To fulfill the valency of each carbon, that is the bonding power of 4, the carbon has a single bond hydrogen. We count round, we see this capacity for 6 hydrogens, 6 carbons, but with alternate single and double bonds. That is the Kekule model. Pause the lesson and represent the Kekule model as a skeletal formula. Come back when you are ready to look at my version. Okay, so hopefully you've had a try. So this is the skeletal formula. If you remember skeletals, we don't draw carbon atoms, we don't draw hydrogen atoms, we don't draw carbon-hydrogen bonds. We will draw carbon-carbon bonds. So our skeletal is literally a hexagon with alternate double bonds, single bond, double bond, single bond, double bond. So we've got a hexagon of carbon-carbon bonds, alternately single and double. So having introduced Kekule, we now need to discuss what are the problems with the Kekule model that lead to the need for a more modern molecular orbital version. Well, the first thing we can say about the Kekule model is that it predicts two types of bond between carbon atoms within benzene. Now, if we can get an estimate of the length of the carbon-carbon bonds, which we can from X-ray diffraction data, and if I share that data with you, we'll see that the carbon-carbon single bond is estimated to have a bond in general, a bond length in general within the hydrocarbons and other molecules of 0.154 nanometers. The carbon-carbon double bond is estimated at 0.134 nanometers. So we would expect from Kekule to see two bond lengths emerging from X-ray diffraction data estimates, but it's found that in benzene all of the carbon-carbon bonds are of equal length, what's called bond equivalence. There are not two lengths of carbon-carbon bonds, and the carbon-carbon bond is found to be of a length that is intermediate, that is positioned between the length of the single and of the double bond. That clearly contradicts the Kekule model. So we can state, and you are expected to explain, perhaps in a 6-mark question, that the bond length data indicates that the Kekule model of alternate single and double bonds must be incorrect. Now, there is another problem with the Kekule model. So this is problem number 2, and there are 3 in total. So we'll work through them. We've gone through the first one. This is problem number 2. And that is that the model, the Kekule model, predicts, because of the presence of 3 carbon-carbon double bonds, it predicts the chemistry of the alkenes for benzene. So I'd like you to pause the lesson and think or look back through your notes on alkenes and be clear in your own mind what is the laboratory test for an alkene. And secondly, what type of reactions do alkenes undergo typically? So pause the lesson, come back when you have either thought that through or researched from your earlier notes. Resume when you are ready to do so. Okay, so the Kekule model predicts the chemistry of the alkenes for the benzene, just to recap. So the test for alkenes in the laboratory is to shake the alkene with orange bromine water. So an aliphatic alkene, we would expect to see rapid decolorization at room temperature. However, benzene, which Kekule proposes to have 3 carbon-carbon double bonds, shows no reaction. Now, the type of reactions that alkenes are assumed to undergo is electrophilic additions. So alkenes react rapidly through a mechanism of electrophilic addition. However, benzene does not show the chemistry of electrophilic additions. Again, that contradicts Kekule's proposed model. So what do we know, or can I introduce you to? Well, the mechanism of electrophilic substitutions, which aliphatic alkenes do not show that mechanism, the chemistry of that mechanism, but benzene does in the presence of a catalyst. So we can conclude that the absence of carbon double bond carbon chemistry indicates that the Kekule model is incorrect. So that's the second inconsistency of the Kekule model. A third piece of evidence contradicting the Kekule model is provided by thermochemistry. So Kekule would predict the thermochemistry one would expect with alkenes, and by comparing that with experimental data for benzene, we find that they do not agree. So the detail would be on the enthalpy of hydrogenation. So comparing the hydrogenation of cyclohexene to that of benzene. So cyclohexene to that of benzene. So the hydrogenation of cyclohexene, let's just show what we mean by that. So there is cyclohexene plus hydrogen. So this is hydrogenation, the addition of hydrogen across the double bond to form cyclohexane. Now, the enthalpy change for that reaction, the enthalpy of hydrogenation of cyclohexene, is minus 120 kilojoules per mole. If that is so, pause the lesson and predict the enthalpy change for the hydrogenation of the Kekule model of benzene. So, hopefully you have thought this through and realizing that benzene, according to the Kekule model, has 3 double bonds. So would, in the case of an addition reaction of hydrogen, would react with 3 molecules of hydrogen to form the same product as for the hydrogenation of cyclohexene. We'll get cyclohexane. Now, what would be the enthalpy change of that? Well, we're going to assume that that will be equal to 3 times minus 120. So for each double bond, adding hydrogen across that double bond releases 120 kilojoules per mole. So we would expect the enthalpy change for the hydrogenation of benzene Kekule model to be minus 360 kilojoules per mole. However, the experimental value is not found to be that. It's found to be only minus 208 kilojoules per mole. You'll find variations in various textbooks, but if I take minus 208, that means that real benzene, the benzene structure that really exists and not the Kekule model, is 152 kilojoules more per mole more stable than predicted by the Kekule structure. So the Kekule structure would predict a hydrogenation enthalpy of minus 360. Real benzene only releases 208 kilojoules per mole. That means that real benzene is 152 kilojoules per mole more stable than the molecule in the Kekule model. Now, what would that look like on an enthalpy profile? So you may be asked to produce an enthalpy profile for the hydrogenation of the Kekule model and then compare it to real benzene. So let's just give you a bit of a prompt. So this is what we mean by an enthalpy profile, enthalpy here, and I've positioned cyclohexane as our molecule here on this enthalpy value. Pause the lesson and place Kekule model benzene and real benzene on that profile. Add in enthalpy change values. Think it through. Come back to get some more prompting if you need it. Okay, so my first prompt would be, okay, I'm putting in the Kekule model here. Kekule model plus 3 hydrogens releases 360 to form cyclohexane. If you haven't already done so, pause the lesson and place actual benzene in that enthalpy profile and add in enthalpy values. Pause, think it through, come back when you are ready to look at my suggestion. Okay, so I would place, not quite to scale, but I'm going to use the representation of hexagon with a circle for real benzene, plus 3 hydrogens. That only releases 208 kilojoules per mole to make the same product, cyclohexane. So, Kekule benzene plus 3 hydrogens makes cyclohexane, real benzene and 3 hydrogens makes cyclohexane. So we can obviously conclude from this that there is a difference between the energy state here, of this enthalpy value here, of the Kekule model and the real benzene, which of course is the difference between the two. So that's minus 152 kilojoules. So we're going to say that real benzene is 152 kilojoules lower in energy, more stable than the Kekule model. Run through that again if you have any hesitations before moving on. So having established that the Kekule model of benzene can't be correct, we move on to using molecular orbital theory to produce a delocalized electron model for benzene. So if Kekule will not do, what is the alternative? Well, we will use molecular orbital theory. If you recall ideas about three-dimensional regions of space occupied by electrons, to form a delocalized electron model for the bonding in benzene. Each carbon within the benzene ring will form 3 sigma bonds. Now, if you're not sure about sigma, I would suggest you pause and review sigma and pi bonding. So each carbon will form 3 sigma bonds to 2 carbons and a hydrogen, and that results in a planar arrangement, which I've attempted to represent there. So each of these is a sigma bond. Carbon-hydrogen sigma, carbon-carbon sigma, carbon-carbon sigma. In this region it will be a trigonal planar arrangement around each carbon, so bond angle 120. But we know that carbon has a 4th electron in the outer shell, and the model proposes that that electron is in a p orbital at right angles to the plane of the benzene ring or carbon ring molecule. So p orbital, if you remember, is 2 lobes, one above and one below the nucleus. Figure of 8 it's sometimes known as, or dumbbell. So each carbon has a p orbital electron. Now those p orbitals are close together and may overlap. So we've got overlapping p orbitals above the plane of the molecule and also below. 2 separate overlapping rings are formed. So we have, if you recall, the overlap of p orbitals is known as pi bonding, so we have a delocalized pi system above and below the plane of the benzene molecule, the carbon ring. And we'll see it represented like so. Here's the carbon ring. We have a ring representing the overlap of p orbitals in a delocalized pi system, and similarly below. Now the electrons can move anywhere within the delocalized pi system, hence they are delocalized. So the electrons within this model are not located or localized to any particular pair of carbons. They are able to move anywhere within the overlapping pi systems above and below the plane of the molecule. So rather than, as in the Kekule model, alternate single and double bonds, the bonding consists of 3 sigma bonds per carbon, and the fourth electron participates in a delocalized pi system formed by the overlap of adjacent p orbitals. That can be represented as I've done here, but more generally and more usefully, that idea is represented by a hexagon with a circle within it, representing a delocalized ring. Please note, rings above and below represent one delocalized pi system. So the fact that they seem to be separated in our minds doesn't mean it is so at an atomic level, and that is one delocalized system above and below. 2 rings, but one delocalized pi system. Now, you may recall there was an energy difference between the Kekule model and the actual benzene. So we're now going to say an energy difference between the Kekule and the delocalized model, and that may be called the delocalization energy, because it's going to become a general principle that delocalized electron systems are of lower energy than localized. So we explain the greater stability of benzene as it is found in experimental data to be due to the formation of a delocalized model of bonding, and that delocalized model of bonding is associated with a lower energy state, and the difference between the Kekule and the delocalized model for benzene may be called the delocalization energy. The delocalized electron model for benzene also explains its relative resistance to reaction with electrophiles compared to alkenes. So if we look here, we'll see, as I've written it out, benzene is less attractive to electrophiles compared to alkenes. In an alkene, we have the pi bond electrons localized, that is, held and retained between 2 specific and particular carbon atoms. In benzene, the model is that the p orbital electron is able to move between any of the 6 electrons above or below the plane. So we would say that the alkene has a localized electron density, and that is much more likely to find its way and be attractive to an electrophile, such as a positively polarized bromine atom. Of course, there may be some attraction for these electrons within the delocalized pi system, but not sufficiently strong for benzene and its derivatives to react to electrophiles without the presence of a catalyst. So having described the delocalized electron model of benzene, we need to move on to naming benzene containing compounds, that is, aromatics. So many aromatic compounds are named as benzene derivatives. For example, nitrobenzene. If we look at the structure, we'll see that it is mono-substituted. The hydrogen that was positioned on this carbon has been replaced by an NO2 group. So it's a mono-substituted benzene derivative. Other aromatic compounds that are named as a benzene derivative include the alkyl aromatics and the halo aromatic compounds. So if I identify 3 methylbenzene, chlorobenzene and ethylbenzene, could you draw the structures? Pause the lesson, draw the structures, come back to check against my answers. So, methylbenzene, as a skeletal structure, we've replaced the hydrogen with a methyl group. Chlorobenzene, very simple, instead of a hydrogen we have a chlorine, so that's chlorobenzene. Ethylbenzene, instead of a hydrogen here we have CH2, CH3, an ethyl group, what's called a substituent. That is, it has been substituted for a hydrogen, a substituent. So these are mono-substituted benzene derivatives. Other compounds, other aromatic compounds, are not necessarily named as benzene derivatives, and we will have a look at some of those. So the other most common type of naming is where the benzene ring is treated as itself being a substituent, that is a substitution into a parent molecule, and in which case it is named, or the benzene ring is identified by using the phenyl labeling. So let's just have a look at a couple of instances in which you will meet phenyl. The first instance would be if the attached alkyl group, the group attached to the benzene ring, the alkyl group, has 7 or more carbon atoms. So here's an example, 3-phenyl heptane. Pause the lesson and draw the structure of 3-phenyl heptane. Come back to look at my model. Continuing, here is the structure of 3-phenyl heptane. So we have a parent molecule 1, 2, 3, 4, 5, 6, 7. So there's our heptane on the 3rd carbon in the chain. We have a benzene ring attached, and we name that as a phenyl. So just as methane becomes methyl, benzene becomes phenyl. Now the second instance where you will meet the phenyl labeling is where the attached alkyl group contains a functional group. So an example for you to try is phenyl ethanoic acid. Do you like to try to draw phenyl ethanoic acid? Pause and come back when you are ready. Okay, so here is phenyl ethanoic acid. So we've got ethanoic acid, but instead of 3 hydrogens on the first carbon, as I've drawn it, we have 2. One of the hydrogens has been substituted for by a benzene ring. So as the attached alkyl group has a functional group, a carboxylic acid group, that is named as phenyl ethanoic acid. There are also some special names inconsistent with the rules that I've just set out that are used by chemists and in textbooks and examination questions. So these you'll need to know as case-by-case naming. The first one would be this molecule. Pause the lesson and think back. Where have you met this before? What's its name? Okay, so this is known as benzoic acid. Benzoic acid. So you've got benzene ring, a 7th carbon, which is itself part of the carboxylic acid functional group. So it is also known as benzene carboxylic acid, but most commonly it's referred to as benzoic acid. What's the name of this? Pause and think about it. Okay, so this is phenylamine. Okay, so we've got an amine group and a phenyl substituent. Instead of NH3, we have a benzene ring, so phenylamine. Most chemists would say phenylamine. Over here, we have hydroxy-containing aromatic. Name it. Okay, so this is phenol. Now, I'd just like to remind you that you will also see phenol drawn like that, as you will with the other benzene rings. It pretty much depends on the flexibility of the chemical drawing program that you are using. But you, as an author or as an exam writer or whatever, so you will see benzene represented as the Kekule structure in all aromatic compounds. That is acceptable, or you will see it as the classic hexagon with an inserted ring. Okay, what about this as our final example of a special name? You might refer to benzoic acid here as your model. What might this be? Pause, come up with a name, compare it to the correct answer. Okay, so here is the correct answer. It's benzaldehyde. Again, it's got the 7 carbons, so benzene ring plus 1 carbon, benzaldehyde, benzoic acid. So these need to be known on a case-by-case basis. So let's now look at further substitutions, by which we mean aromatic compounds in which more than one hydrogen has been substituted for by another group. So if we take the molecule that I have here, we've got a benzene ring, we had the nitro group, but on a second carbon the hydrogen has been substituted for an NO2. We have 2 substituent groups. In this case, they are the same. Now, what would be the name of this? Well, it's going to be nitrobenzene. But there's 2 nitro groups, so it's going to be dinitrobenzene, and we need to position them. So we're going to call this carbon number 1, this carbon number 2, this carbon number 3. So it's 1, 3 dinitrobenzene. Pause the lesson and name the 2 nitro aromatics that have been revealed. Okay, so what do we think these are? Well, this is going to be 1,2-dinitrobenzene. So the benzene derivatives, carbon number 1, carbon number 2. And here, well, this is going to be trinitro. We've got 3 nitro groups, and 1, 3, 5. 1, 2, 3, 4, 5, 6. So positioned on number 1, number 2, sorry, number 1, number 3, number 5. Slip of the tongue. So 1, 3, 5 trinitrobenzene. So where there are more than one substituent, we need to put the relative positions on the benzene ring by numbering. So we decide on which is going to be carbon number 1 and go from there. Try these 3. Pause the lesson, come back when you are ready to discuss. Okay, so let's have a look at the molecule, the aromatic on the left. Well, we've got a carboxylic acid group, so I'm going to go for benzoic acid, and if that's my naming stem, well then this is carbon number 1 and this will be carbon number 2, so I'm going to say 2-hydroxy-benzoic acid. Alternatively, 2-hydroxy-benzene carboxylic acid. So perhaps I should introduce that naming. It is quite common. So 2-hydroxy instead of benzoic acid, you might see benzene carboxylic acid. But by naming it as a carboxylic acid, this becomes carbon number 1. Hence, this is carbon number 2, so 2-hydroxy. Okay, if that helps you with the other two, pause and come back when you are ready. Okay, so let's move on to the middle molecule. So I'm going to name this as a phenol, so that decides that where my laser pointer is carbon number 1, so 2, 3, 4, so on the 4th carbon there's a methyl group, so 4-methyl phenol. And try the 3rd example if you haven't already done so. Here's my answer. So 3-chloromethylbenzene. I'm going to decide that this is carbon number 1. So 2, 3, 3-chloromethylbenzene. There is in IUPAC naming an order of priority on substituents, but we're not going to go into that. That is 3-chloromethylbenzene. The typical reactions of aromatic compounds are electrophilic substitutions. So the typical reactions of benzene and its derivatives involve electrophilic substitutions in the ring rather than electrophilic additions, which we see with alkenes and other unsaturated molecules. Now, the reasoning for this is that in substitution, the relatively stable benzene ring is present in the product. So that is energetically favoured compared to the reaction product of an addition reaction in which the product no longer has the benzene ring. So the crucial thing is that in electrophilic substitutions, the benzene ring is retained in the product. So there are 3 examples of electrophilic substitutions that you are meant to know about for OCR A. The first one is the nitration of benzene to form nitrobenzene. So here is a molecular formula for benzene, C6H6. Here is a molecular formula for nitric acid. We're going to form nitrobenzene. Could you predict the product side of that reaction equation? Think about it carefully. Think about balancing. Come back when you have a solution. Okay, so here is my solution. We've got C6H5NO2. Remember, we have replaced a hydrogen from C6H6, so we're now down to C6H5 with a substituent nitro group, so C6H5NO2. And the balancing should help you predict water as a product. Don't forget to balance these equations. One of the most common ways that candidates lose marks in the end exam is by knowing the chemistry of nitration of the benzene ring, but not bothering or forgetting to balance the equation. So I make that point at this stage, and I hope that it'll be taken on board. So what if we represent that as a skeletal, and so we're mixing skeletal with molecular formula here. Could you draw the skeletal or a structure for the product, the nitrobenzene? Pause, come back when you are ready to look at my model. Okay, so here is nitrobenzene. A hydrogen has been replaced by the NO2 group, and we see that I haven't forgotten to balance the equation with water. Now, at this stage, you know that you will need to know the conditions. So the conditions, the first one vital, is the presence of a catalyst, concentrated sulfuric acid. Now, catalysts and other conditions are often written above the direction of change arrow. So if you see that in a textbook or an exam question, that's simply telling you about the conditions. So concentrated H2SO4 above the reaction arrow, that is not a reactant, it is a catalyst. So it may take part in the reaction, as we will see when we do the mechanism, but it should be regenerated at the end. The second condition you need to know is concentrated nitric acid, not just nitric acid, but concentrated nitric acid. The combination of concentrated sulfuric and concentrated nitric is known as the nitrating mixture. And lastly, an important temperature, 50 degrees Celsius. Must be up at about 50 for a decent rate of reaction, but should not exceed 50 for reasons we will go into on the next few slides. So, moving on to the mechanism of nitration, which of course is an electrophilic substitution. And the first step in the mechanism is the generation of the electrophile. We have the reactant, nitric acid, and the catalyst, sulfuric acid. That catalyst will be regenerated as the last step in the mechanism. If you've seen this before or you feel inspired, write the products on the right hand side. Come back when you've had a go. Okay, so if I reveal the products, we'll see that we've got hydrogen sulfate ion. So sulfuric acid is acting as a Bronsted-Lowry acid, donating a proton to hydrogen nitrate, leaving behind the conjugate base, the hydrogen sulfate ion. The protonated hydrogen nitrate decomposes to form water and the nitronium ion. So the nitronium ion, I will write out. And that, of course, is our electrophile. That is the electron pair acceptor. Now, if I move the electrophile to meet benzene, could you pause the lesson and draw an appropriate curly arrow for this stage? So, if I put in a curly arrow, I'm going to start on the benzene ring, the ring of the pi system, and I'm going to end up close to the nitrogen where the bond is going to form between the carbon here and the nitrogen. So I'm positioning my curly arrow like so. Okay, so if that is the electron pair movement, could you draw the product of that electron pair movement? Pause the lesson, think it through, come back to check against my model answer. Okay, so we are going to form a bond between the carbon at 2 o'clock and the nitro group, but we're also going to now draw in the hydrogen that we didn't draw in on the first carbon here, because this is a skeletal diagram. So the carbon here is bonded to a hydrogen, but we don't draw it because on the left hand side it's a skeletal. But we need that detail for this mechanism. So here I've got a covalent bond between the carbon and a hydrogen. Now if that's so, the carbon here has 4 covalent bonds. It can no longer take part in the pi system. So instead of a complete circle, I now have an incomplete delocalized ring of electrons, which has lost some electron density, so it's now positively charged. Now we know from my earlier explanation that substitutions result in the retention of the delocalized ring of electrons. So we need to restore that by taking the electrons from this bond and returning them to the ring. If that is the electron movement that's going to come from that intermediate structure, can you predict the product? So here is the product, nitrobenzene, but what have I forgotten to include? I hope you remembered. We are going to have a hydrogen ion. This hydrogen here must not be forgotten. It used to have an equal share of a pair of electrons in a covalent bond. It no longer has. It is now a positively charged hydrogen ion. So we have retained the balancing of the equation for charge. So on the left hand side here with the reactants, the first stage here, we have got NO2 plus, we're overall 1 positive, so our end product must also balance for charge and be overall 1 positive. But I mentioned earlier that H2SO4 is a catalyst, so can you now write the equation for the regeneration of the catalyst? Pause the lesson and check against my model. Okay, so HSO4 minus from the list of products here, HSO4 minus plus H plus regenerates the catalyst H2SO4. So the catalyst is regenerated. That is generally worth about 5 marks at A level, but you must get all of the detail correct, including the start and end points for your curly arrows. Now, it's also possible for nitration to continue past the mono-substituted derivative. And let's take an example here, C6H6 for benzene, not reacting with one nitric acid, one hydrogen nitrate, but with 2. So we're going to form a disubstituted product. Can you complete the equation writing a molecular formula? Pause, come back when you are ready. Okay, so if we have a look at the product, we've lost 2 hydrogens. We originally had C6H6. The hydrogens are substituted for. Okay, so we've lost 2 hydrogens and we've acquired 2 nitrogens and 4 oxygens in the form of 2 nitro groups. The balancing, looking at that, it's 2 H2O. So the molecule that will form, of course, is 1,3-dinitrobenzene. And I've got 2 waters here floating about to balance that equation. Now, the difficulty or problem I need to highlight to you about 1,3-dinitrobenzene or other nitro derivatives are that they are potentially explosive. And you may have heard of TNT, trinitrotoluene, trinitromethylbenzene, well-known commercial explosive. So to avoid the potential production of dinitro and trinitro products in the nitration of benzene in the school laboratory, we carefully control the temperature to 50 degrees Celsius. Temperatures above 50 may produce small quantities of the di and tri substituted product. So we prevent that by keeping the temperature to 50 degrees Celsius. So further nitration is prevented by careful control of the temperature. So let's look at the second electrophilic substitution on the specification, the formation of halobenzenes. For instance, chlorobenzene from benzene and chlorine. Complete the product side of that equation. Come back to check your answers when you've done so. Okay, so we've substituted a chlorine for a hydrogen. So we're now C6H5Cl. Balancing the equation, we'll see that we have HCl as the second product. If we write that out in terms of some structural formulae and diagrams, we'll see that we've got chlorobenzene with HCl. Now, we need to know the conditions, gaseous chlorine, and crucially a catalyst. So electrophilic substitution, as I mentioned right at the start of this lesson, requires a catalyst. So aluminium trichloride or iron trichloride. Again, we might write the catalyst above the reaction equation arrow. However, just a point here, if for instance we weren't adding bromine, but we weren't adding chlorine, but we're adding bromine, then the catalyst would be iron 3 bromide, and so on. Same for iodine. So there has to be an agreement between the halogen and what's called the halogen carrier, the catalyst halogen carrier. So bromine, we need iron tribromide as catalyst. Chlorine, the halogen carrier, is iron 3 chloride. We also need to consider the mechanism of halogenation, and of course, just as with nitration, we need to consider the same points. That is, of course, the generation of the electrophile. So chlorine interacts with the catalyst. I've chosen aluminium trichloride. An acceptable simplification at A level is the formation of a Cl plus particle, a positive chlorine particle, and the aluminium tetrachloride complex, which is negatively charged. So the Cl plus, the positively charged chlorine particle, is the electrophile. As I said, this is a simplification at A level that is accepted by all examples. If I put the electrophile and benzene together, could you pause the lesson and write in or insert the correct curly arrow? Come back to check against my answer. Okay, so my curly arrow starts on the delocalized pi system and finishes close to the chlorine. A little bit wobbly, but it will do. If that is the case, could you draw structures for the intermediate molecule formed? Pause the lesson, come back when you have done that. Okay, so let's have a look. So we're going to form a bond between the carbon and chlorine. We now remember that we've got a hydrogen on this carbon. We don't draw it on the left hand side because it's a skeletal structure for benzene. We draw an incomplete, that would not be acceptable, so we've got to draw an incomplete delocalized ring of electrons and add a positive charge. A pair of electrons have been lost to form this bond here. Okay, it's come out, so we are now just got a share of that pair of electrons rather than sole possession. But just as with nitration, we need to restore the delocalized pi system and return electrons by breaking the carbon-hydrogen bond here. If that's the case, could you pause the lesson and predict the products of that electron pair movement? Okay, resuming, here is chlorobenzene, of course, and I've left out, as previously, I'm hoping that you'll have remembered, we also got a hydrogen ion as our product. The hydrogen here is shed as, or substituted for, by a chlorine, and leaves as a hydrogen ion. But we need to regenerate the catalyst. Could you attempt an equation for the regeneration of the catalyst? Pause the lesson and come back when you are ready. Okay, so the regeneration of the catalyst, well, we take the aluminium tetrachloride complex here, plus a hydrogen ion generates hydrogen chloride, and a aluminium trichloride is regenerated as the catalyst. There are two other reactions you need to be aware of to further electrophilic substitutions of the benzene ring, but for which we don't need the mechanisms in OCR A. So they are both labelled Friedel-Crafts reactions after the chemists that came across them. The first one is the Friedel-Crafts alkylation. So this involves benzene and some alkyl groups such as methyl, ethyl, etc., but the haloalkane, so bromoethane, chlorobutane, etc. Now, this has a very similar mechanism to halogenation. So, thinking about halogenation, pause the lesson and predict the products for the reaction between benzene and a general haloalkane. Pause and come back when you have had a think about it. Okay, so again, it follows the pattern of the haloalkane reaction in that the chlorine joins with the hydrogen that leaves the benzene ring, and the rest of the molecule, the R group, is substituted into the benzene ring, so it becomes a substituent on the benzene ring. So we have 5 hydrogens and the alkyl group R. So let's flesh that out a little with an example like this. So here's benzene and here's chloromethane. There's the pattern. Can you apply it to this example? Pause, think it through, come back when you have an answer. Okay, so what we're going to do is going to break the carbon-chlorine bond here. The chlorine's going to come off as hydrogen chloride, and the R group, the alkyl group, the CH3 group, is going to bond directly to the benzene ring. So we've got a carbon-carbon bond being formed. Now, of course, if it's similar to halogenation, then the catalyst is iron 3 chloride. So the catalyst being iron 3 chloride implies a similar mechanism to halogenation. OCR A does not require prior knowledge of that mechanism, so we will move on without discussing the mechanism, except to say, because the catalyst is iron 3 chloride, it's got to be similar to the mechanism of halogenation. So we're going to move on to Friedel-Crafts acylation. So acylation, you're going to add to the benzene ring not a saturated carbon chain, but a carbon-oxygen double bond, an acyl group that is then bonded to a alkyl group. So we've got an acyl chloride, and we're going to get rid of the chlorine and bond directly between the benzene ring and the carbon of the carbonyl group there. So the equation would look something like this. Benzene RCO, so that's R double bond oxygen, R carbon double bond oxygen, carbon chlorine, so that's an acyl chloride, and that will form an aromatic acyl compound, hydrogen chloride being produced as the waste product. Following this pattern, looking at this example, could you draw the structures or the structure of the aromatic compound formed? Pause and come back to compare your answer with mine. Okay, so we've lost the chlorine from here. The chlorine ends up in hydrogen chloride. A hydrogen has been lost from this carbon, so carbon-carbon bond formed. So the carbon of the carbonyl bonds directly with the carbon of the carbon within the benzene ring. It's an electrophilic substitution. The catalyst is iron 3 chloride, so we can assume a similar reaction mechanism to halogenation. It will be useful to review the 4 electrophilic substitutions of benzene that we have met in the OCR A specification. So let's look at 1, 2, 3, 4 examples, predict the products and also propose a catalyst for each electrophilic substitution. Pause the lesson, come back when you have completed that task. Okay, so if I reveal the first set of answers, then we have from chloroethane, we have the ethyl group substituting into the benzene ring. Don't forget to balance your equation with the waste product, HCl. The catalyst, aluminium trichloride or iron 3 chloride, either will do. So, revealing the second set of products, this of course is a nitration, concentrated nitric acid, catalyst concentrated sulfuric acid. The nitro group, NO2 group, is substituted into the benzene ring and we balance the equation with water. The third electrophilic substitution is a Friedel-Crafts acylation, so we have an acylated benzene ring. For instance, this could be, if this was CH3, this would be phenylethanone. Hydrogen bromide, because we're starting with an acyl bromide. If we're starting with acyl bromide, then the catalyst is aluminium tribromide or iron tribromide. The fourth, this is halogenation. We're substituting a chlorine into the benzene ring. Hydrogen chloride is the waste product. The catalyst, either iron 3 chloride or aluminium 3 chloride. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.